know where that table is right here to help you with simplifying. Make sure you've got that chart here. So we're on example 3 right now. We're looking to start writing radicals in what, kids? Simplest form. Now it says write each expression in simplest form. And if I go back to my notes from yesterday when I said, well, if there was a vocab word that I thought was really important to know, it was going to be this one right here. There's 3 rules that you kind of have to remember. Okay, it says no radicands have perfect nth powers as a factor other than what? 1. No radicands contain, and no radicals appear in the denominator of a fraction. This next example we're going to look at, what's it say, the cube root of 500, is that right? Mm-hmm. Looking to simplify the cube root of 500. Here's how this is going to work, kids. What we need to do is ask ourselves this. In that example, cube root of 500, we need to say, all right, is there anything I can take out of 500 that's a perfect, what's the index up here for this simplification problem? 3. Is there any number I could factor out of 500 that is a perfect cube other than 1? Exactly. So what I'm going to do is this, kids. What are we trying to simplify here? Cube root of 500. So I'm going to jump into my chart right here, and I'm going to say, okay, in this chart, I'm going to look at the cube root values, and I'm going to ask myself, is there a number other than 1 that divides evenly into 500? Okay? Who's willing to check 500 divided by 8 for me? Ellie, you got 500 divided by 8. Who wants to check 500 divided by 27? Belle, Maddie, you do 64. Volunteer for 125. Carly, anybody want to do 216? Got it, Tessa? Yeah. Volunteer for 343? I'll do it first. Okay. Do I need to do 512? Because I've gotten past 500. All right. I want to know if anybody has taken anything. Why am I choosing the cube column? The index was what value on that root that we're trying to simplify? 3. Okay. Anybody have a value that goes evenly into 500 right now that you were given or chose? Who has the 8? Ellie, did that work? No. No? Who had 27? Did that work? Who had 64? Did that work? No. Who had 125? Did that work? 125? 400 divided by, I want you to do 500 divided by 125. But it still worked, right? Yeah. Okay, is there anything bigger than 125 that worked? No. Who had 216? Okay. That didn't work. Nope. Who had 343? Did that work? No. What perfect cube is going to divide evenly into 500? Carly, how many times? 4. Okay, so what we could say is this. Hey, when we check this perfect cube column right here, to simplify this, this is what you need to do. We say, I could write this as the cube root of, what perfect cube went in there again, Carly? 4. What perfect cube went in there? 125. How many times? 4. You guys agree that that's one of the rules. That's a product of radicals right there. Same index. I can break it down as the cube root of 125 times the cube root of 4. And I can use the cube root of 125 because isn't 125 a perfect cube? What is the cube root of 125 then if I look back at my chart, kids? Well, if I follow 125 back, what x value does it correspond to here? So this value here on the left, right here, this is what value now, kids? I've taken the perfect cube, I've factored out the perfect cube of 125 from the cube root of 500. So this is simply going to be 5 times the cube root of what, kids? That's simplest form right there. 5 times the cube root of 4. Okay? We were able to factor out a perfect cube other than 1. Okay? All right. You guys try this one on your own. I'll make up one. You guys try that on your own. simplify that as best you can. First of all, which column are you checking to see if you can factor out? Okay, so you're going to check the cube count. So see if there's a perfect cube that factors into 128. You may have a solution for me. Jazzy, what'd you come up with, kid? 2 times the cube root of 16. Okay. Anybody have anything different? Belle? All right, so this is an interesting one. Jasmine, what perfect cube went into 128? 8 went in there. Did 8 go in there? Yeah, it did. I don't disagree, it went in there. So you wrote yours as the cube root of 8 times the cube root of 16. Very good. I like that. Okay. Belle, talk to me. What did you do? Did you find it 8 went into 216? Or I'm sorry, into 128?
I started at the top and then went down.
Oh gosh, you're way ahead of me. All right. So one thing that I want to touch on right here, and you're exactly right. Jazzy, I don't disagree with what you did there. Okay, I don't disagree with what you did at all. You started with low numbers and worked your way up until you found one, right? Okay. This is a suggestion I want to make to you. Instead of starting low numbers and working up, and Belle's already way ahead of me, so she should obviously be teaching the class instead of Parson, okay? What I want to tell you is this. What ends up happening here, Jasmine, is this. It turns out that from this chart, it turns out from the cube chart that both 8 and what else went in there, Jazzy, or Belle? 64 went in. So what I'm going to tell you is this. What value was I talking about checking? Cube root of what were we trying to simplify? Was it 128?
Yeah.
Okay. Start high and work your way down because we want to be able to take the biggest perfect root out as possible. So 128 was our value, right? So what really could be the biggest perfect cube that I could check to see if it went in there? You would say, well, 125. But is 125 going to go evenly into 128? No. Then the next one I'm actually going to check is what? 64. So instead of starting low and working your way up when you factor that stuff out, I actually want you to start high and work your way. Okay. Once I checked 125 and it didn't work, what would be the next lowest perfect cube to check, kids? The 64 go in there, Belle. How many times did it go in there? 2. Okay. So you wrote this as the cube root of 64 times the cube root of 2. Is that correct? Okay, but the cube root of 64 is what value? Okay, I don't disagree. Now, Jasmine, we could have gone a step further. You could have asked yourself this. You knew the cube root of 8 was 2, right? Ask yourself, are there any perfect cubes that still go into 16? Well, what did you use the first time? You could have written this as 2 times the cube root of 8 times the cube root of 2 again. What's the cube root of 8 again here? So you're back to 2 times 2, which is 4 cube roots of 2 there. Okay? Make sense? All right. Very good. Very good. So the answer here really should be what, kids? 4 times the cube root of 2. Very good, kids. Very good. All right. Well, that said, let's look at this next example. And this next example concerns me a bit. If you look at your notes back on that first page right here, it says no radicals appear where, kids? In the denominator of a fraction. We've been talking about this first bullet right here. No radicals have perfect nth powers as factors other than 1. So we've been working on taking stuff out. But now we're in a situation we don't want any radical sign to appear where? All right, next one right here. If you look at this right here, where do I have a radical sign? Well, I have it in the numerator. Is having an enumerator okay? Yeah. How about down here? Is it okay I'm down there? No. Okay. Well, a couple ways I handle this. The first thing that we're really going to look at, and like I said, I'm concerned about this one, how to simplify stuff like this. Here's how this is going to work, kids. First thing you want to look at is your denominator down here. If you ever have a radical in the denominator, that's a red flag. That's bad news. Okay? So we're going to look to simplify this, and here's how we're looking at this. First of all, in that denominator where that radical is at, what is the index for that radical? What's the index there? 4. So what we need to do, kids, is look at our fourth power chart. So I'm going to go back into this chart right here. Here's my fourth power chart. Kids, does 4 show up in the fourth power chart at all? Ooh, so there is a fourth root, but it's just not going to be a very nice number. Okay? So here's how you handle this. All right? What you start to do is say, okay, are there any values here where I could say, well, we have that fourth root, oops, we have that fourth root of 4 times the fourth root of something right here would equal a perfect value in this row. In other words, gosh, if 4 doesn't fit in this chart, what's the next number above 4? In this chart where it's x to the fourth. Where would 4 fall between, in other words, in this fourth power row or column? Between 1 and 16, okay? Well, 4 times something's not going to make 1, okay? Because it's not going to work. You've got to work our way up. Is 4 a factor of this value 16? Ooh. How many 4s do you need to make 16? Okay, watch what I do here. The fourth root of 16 is something we want to think about because 16 is a perfect fourth root. Okay? So the question becomes this. If this is what's in the denominator, and I really want to get to my first perfect fourth root right there, what must go in right here? In other words, the fourth root of 4 times the fourth root of what makes the fourth root of 16? Fourth root of 4. So this unknown here is going to be a 4. So what we're really going to do, kids, is we're actually going to rationalize this by multiplying a form of 1. Okay? What I'm going to do here is multiply both the top and the bottom. Do you guys agree multiplying by 1 doesn't change the problem at all? If I take something times 1, am I changing its value? No. So do you guys agree that I'm going to multiply the bottom by the fourth root of 4, and up top times the fourth root of 4. Okay, first of all, aren't these values in the numerator and denominator the same? So I'm really multiplying by what? 1. I'm not changing it. So here's what you end up with, kids. What's 19 times 4 here, kids? So this becomes the fourth root of 76 over the fourth root of what? Now, why did I do that? Again, here's why I did that. I said, well, we're dealing with fourth roots. We got to get something in the denominator so we make that radical sign go away. We were at 4, and we said, you know what? The first possible perfect fourth power value is 16, and I know 4 times 4 is 16. Kids, what is the fourth root of 16 now? 2 by this chart right here. So what can I change the denominator to? What value here, kids? Okay, so I could call this the fourth root of 76 over what? I don't like the way I wrote that. Hang on. fourth root of 76 all over what? Okay, quick question. Did the radical sign leave the denominator that way? Did the radical sign leave the denominator that way? Is that a good thing or bad thing? That's a good thing.
I'm sorry, can you just repeat how you got the 2?
Somebody tell me where the 2 came from. You have your calculator handy, kiddo?
Yeah.
Punch in the fourth root of 16 now. Getting that? Or if the way I read this chart, P, and maybe I'm doing a bad job, but the 16, that 16 was the value we chose in the fourth column, right? If this is x to the fourth, then the x value, or the fourth root of it, is from this chart what value over here?
Oh, okay.
It's coming from that far left value in the chart, too. Okay, you good with that, kiddo?
Yep.
Great question. All right, now are we done? The question is, are we done? I don't know, because there's a chance that we could still simplify one other part. Even though I've got the 2, no radicals in the denominator, there's still a chance I could simplify what? The fourth root of 76. So let's check. What would be the first value I could check to even see if a perfect fourth power went in there? Can I check 81 to see if that goes in 76? Can I check 16?
Yes.
Somebody take 76 and divide by 16, see if it goes in there.
No.
Nope. Gosh, 1 looks like it's the last one, so can 76 be broken down into a product of perfect fourth power values? No. So are we done now? Okay, so your solution to this, simplest form, would be the fourth root of 76 all over what, kids? 2. Oh, my Lord. You guys are absolutely amazing. Absolutely amazing. That's pretty upper level stuff. I bet if we walked up to you and I, walked right into Wright Hall and said, here, solve that. There's a lot of kids sitting in college at UNI today. They'll probably look at that and be like, I don't know. But you, my little stars, could go in there and tell them how to do it. Did you make a field trip today? We can stop at Village Inn when we're done.
Down.
Down?
Yeah.
I mean, down, does that mean no?
Does it mean
Like
yes?
thumbs down, is that what you're
That
saying?
means yes.
I was saying up, up. That's awesome. Village Inn sounds good to me. All right, kids, what do you think about those 2 examples? I want to tell you this again. Yesterday I said this. Are you going to be able to probably get by doing everything without notes? Well, as good as you guys are, probably. But if you're not sure, where can you refer to for examples? Okay. All right, let's look at example 4. Let's look at example 4. Village Inn. Kiana, why'd you have to bring that up? What'd you do that for? Oh, I did?
Yeah.
I forgot I did. But it's still ingrained in my brain. Now I'm hungry, guys. Okay. Example 4, writing a radical expression in simplest form. Let me ask this question. Where don't you want a radical sign at?
Bottom.
Do I have a radical sign in the denominator? Is that good or bad? That's very bad. This is bad. This is very bad. Okay? Not only is just that radical in the denominator, is it just a radical by itself, or is there something else lingering down there too? It's like the Grinch and his dog in the denominator right now. It's not good. The Grinch is the root of 7. The negative 2 is little Max running around. Anybody been to the movie? Yes, the animated one? Good stuff. Good stuff. Okay? We need to make that go away. We need to make this problem happy. Okay? I want you to write a word down here, kids. Conjugates. When you see this right here, when you see a root in the bottom and that's plus or minus something right here, I automatically want you to think conjugates. We're going to multiply by what's known as conjugates. So in a denominator, we need to fix that. When you have a root down in the denominator and it's added or subtracted something, we get rid of that by multiplying by the conjugate of the denominator. Okay? Now, help me recall what a conjugate is. If the denominator is root 7 minus 2, then what's the conjugate of root 7 minus 2? It's root 7 plus 2. So we're going to multiply a form of 1, where that form of 1 in the numerator and the denominator is the conjugate of the original denominator. So we're going to multiply this by, here's what happens, kids. Root 7 plus what? And root 7 plus Okay, I strongly, strongly encourage you to do this. Put parentheses around stuff. Watch what happens. It's pretty magical, okay? Just like in the Grinch, magic happens. It's so cool. First of all, up top, what's 1 times the square root of 7 going to be when I distribute? This is going to equal the square root of 7 plus, what's 1 times the 2? Hey, is it okay to have square roots up top? Absolutely. We just don't like square roots where? In the bottom. And when I have the square root of something plus something, or the square root of something minus something, we use a form of 1 in conjugate form to try and get rid of that. So now we're going to go ahead and apply a mathematical process, which I got to believe is probably your favorite 4-letter F word.
Factoring?
Not factoring. That's more than 4, Piper.
Oh
Okay.
my God, it's been a long day.
Is today the 5th?
Yeah.
I figured you out. You have your odd days on odd days, and you have your good days on even days.
You know
all
what?
right?
You got me all figured out.
I know. Okay. So make sure you're here tomorrow. It'll be a good day.
Yes.
All right. Hey, we're going to FOIL this out. Okay. Let's go root 7 times root 7 here, kids. Root 7 times root 7. That becomes the square root of what? What's 7 times 7?
49.
But the square root of 49 is really what? So root 7 times itself is really just going to be what? 7. Okay, now watch what happens. This is interesting. I'm going to go to a different color here. I'm going to take root 7 times what, kids? Positive 2, right? So this becomes plus 2 times the square root of 7. Are you with me so far, kids? Okay, so I factored the roots, or I'm sorry, I FOILed the root 7. I should say I've distributed the root 7 to the right. I need to multiply everything here now by negative 2. What's negative 2 times root 7? Okay, and then negative 2 times positive 2, kids. Okay, here's the deal. Are there still radicals in the denominator after I FOILed that out? But we're headed to something that says we're going to have like radicals. What's 2 root 7s minus 2 root 7s? They go away, don't they? They cancel. They're opposites of each other. So really what you're left with in the denominator when this cancels this is 7 minus what?
4.
So up top here, we have root 7 plus what? All over what? Okay. Question that I want to ask now is this. First of all, have we gotten rid of the Grinch in the denominator? It's gone. And what did we use to make that root 7 minus 2 go away? We use conjugates. We multiply by the conjugates of the denominator in a form of 1. So you tell me, are we done? There's no more radical in the denominator. Is there anything we should check yet? What do you want to check on the top? The 7. Better to see if the 7 can be factored down by a perfect. What index is really here even though it's not listed? Okay, let's check it, kids. In my chart, I'm going to jump into the squared column right here. Let's see, 7 is what I'm dealing with, so the first value I can check is 4. Does 4 go evenly into 7? No. And 1 will, but 1's not going to change it. You never need to check 1. So is there any perfect square that could break 7 down further for us? No. No. So are we done? Good. We're done. Very good. That's tough stuff right there, kids. If you see like a root plus something or root minus something, what do you automatically want to think here, kids? Think conjugates right off the bat, okay? All right, page 3 there. Or is that page 4? I can't remember. Okay, let's jump to the next page and see what we can accomplish. Adding and subtracting like radicals and roots. This isn't too bad. The first 2 are pretty easy. I would put a star by the third one. Third one's going to get a little difficult. Okay? So, like radicals occur when both the index of an expression or a value and the radicand of an expression of the value are the same. So in that first example, I have the 6th root of 17 plus the 9th root of, or 9 times the 6th root of 17. Okay? Are the indices the same in both of those radicals? Yep. Is the radicand the same in both of those expressions? Okay. How many sixth roots of 17 do you really have here? 1. So what's 1 of this mess plus 9 of this same mess? How many messes are there? So I could call this 10 times the what root? Now the question becomes this: am I done? Am I done? Am I done? Am I done? Now go figure. There would be a sixth power here. Our table line went up to what power? Fifth power. Okay, can I just tell you this? 1 to the 6th is 1. You want to know what 2 to the 6th is equal to? 64. 64 would be the next value. 64 already surpasses 17, doesn't it? So is there going to be any perfect sixth root for 17 that can factor out of that? No. So we are done. Anybody want to take a guess on what the next one looks like, or what the next one might be? Go ahead, Braden.
What happened to the 9?
What happened to the 9? What happened to the 9, kids? How many sixth roots of 17 did I really have here? 1 plus 9 of them would make how many sixth roots of 17s, Braden? Make sense? So I have 7 to the 1/3 and 7 to the 1/3. Quick question: isn't 7 to the 1/3 the same as the third root of 7, kids? So really, are the indexes the same? Yeah. Are the radicands the same? Yeah. So if you have 5 times 7 to the 1/3 and 6 7 to the 1/3, how many 7 to the 1/3 do you have here, kids? How many? So I could call this 11 times 7 to the 1/3, or you might want to write it as 11 times which root of 7? Okay, either one works. Oh boy. Then we get to this next one. Oh my gosh. How am I going to simplify that? How am I going to subtract to simplify that? I don't know. First of all, are the indexes the same?
Yes.
But are the radicands the same in that last example? That's a problem, right? Okay, which one's bigger?
48.
So what we're going to do, kids, is we're going to try to break that root of 48 down and see if that breaks down into a root of this possibly. So here's the deal. We need to jump into which column in our chart? Fourth column. Okay. I want you guys to check and see in the fourth column, what would be the first value you would check to see if it goes into 48? 16. Check and see if 16 goes in there. How many times?
3.
Oh. So since these don't match right here, the fourth root of 48 and the fourth root of 3, what I could say is, well, what if I could rewrite these two expressions? And honestly, this 48 breaks, how many times did that 16 go in there?
I think it's
Ooh, watch this. This is so cool. Let's see, is there a perfect, if there a perfect fourth power value that goes into 3? Well, no, because the lowest one I could really check is what? I could check 1, but we don't need to check 1. 16 already surpasses the 3, so that's done. So here's what we have, kids. But this is pretty interesting. We took 16 out because 16 was a perfect power of what? 4, right? Look at your chart. What is the fourth power, or I'm sorry, the fourth root of 16? 2. Okay? This is really the same as 2 fourth roots of 3 minus the, really, how many fourth roots of 3 over here? Isn't it? Yeah? No? Yeah? So what's 2 fourth roots of 3 minus 1 fourth root of 3? 1 fourth root of 3 is my solution. How radical is that? That answer's pretty radical, you know it. Yeah.
In the second row right after 16, where'd you put the 3?
This one?
Yeah.
Well, if you break 48 down, it turned out that that perfect fourth power, 16 divides into 48 3 times. That's where that came from, Maddie. Right? Great question. Oh, this is so cool. I love this stuff. I get so excited about it. Geeked up. There's only one thing better than this. Little chin. Right, Sam? Sam doesn't share my enthusiasm, folks. And that's okay. I'm going to keep on keeping on. Let's go to 6. Simplifying variable expressions. All of a sudden we have roots and we have stuff underneath. Okay, here we go. I love this stuff. Okay? Kids, when you start doing stuff like this, this is what I want to tell you right here. 27d to the 12th. What root are we taking? If I had to change the third root to a rational exponent, taking the third root of something is taking it to what power, really? The 1/3 power. So what I can say here, kids, to simplify stuff like this is say, all right, well, this is really 27d to the second, all to what power, kids? Well, 1/3. And what this becomes is a product of a power. This becomes 27 to the... yeah, thank you very much. So right there's a 12, right?
Yes.
Do I have it right now? It's supposed to be an odd day. I'm glad you're back on track. Okay, so this becomes 27 to what power first, kids? Isn't that 1/3? Would you agree with that? And then how about 1/3 of 12 here, kids? D to the 4th. Now, kids, 27 to the 1/3. That's like the cube root of 27. Oh. If I look at my chart here, isn't 27 kind of a perfect cube? What is the cube root of 27? So this is simply going to turn into 3 times what? To the... Okay, you guys try the next one on your own. The 4th root of x to the 4th over y to the 16th. You should easily get this. You're going to rewrite that as x to the 4th over y to the 16th to the what power? Yeah. Because that's a rule that says if your index is 3, it's the same as taking it to the 1/3 power. Okay? So what power are you going to take everything to in your quotient there? If you're looking for the 4th root, kids. 1/4, okay? I'll give you about 3.14 seconds to finish this. Jasmine.
What was the power on the one we just did?
The power?
Yes, like 3D to what?
3d to the 4th, because 1/3 of that 12 is going to be 4, right?
Yeah.
Okay. Simple. Simple. Anybody have an answer? What do you think, P?
X to the first over y.
Yep, because this simply becomes x to the 4th all over y to the 16th, all to what power, kids? Kids, when we bring that power in, what's 1/4 of 4? X to the 1st. What's 1/4 of 16? Right? Right? Okay, so let's move on to example 7. What?
You want us to answer the other one?
Oh, you don't have to answer. I was just being silly.
Oh, okay.
Do you have an answer for that? What is it? A lot of stuff. I love it.
My Chromebook's gonna die.
Your Chromebook's going to die, though. That's not good. It'll be a funeral later on.
It's a
So
bad day. I'm telling you.
we're going to have a Chromebook funeral.
Talking talking about a few.
All right, kids. Here we go. Things are going to get a little
Oh no.
more difficult again. Okay. It says write each expression in simplest form. Assume all variables are what, kids? Positive. All right. This is where things get quite interesting for us, and I think what I want you to do is to write things with fractional exponents here. Let's just look and see what they did here. First one we're going to solve is the cube root of 2a to the 13th, b to the 3rd, c to the what, kids? Okay. You want me to make this easy on you, or you want me to make this hard on you?
Easy.
Okay.
Medium.
Okay. Here we go. You ready for this?
That is true.
Okay. What you're going to do, kids, is you're going to kind of look at this. I'm going to boom this up a little bit. Okay. When you look at this right here, really, how many terms are there down here underneath the radical sign? Okay. So here's what we're going to do. We're going to ask ourselves how many perfect cubes I can take out of each term. Now, kids, the first term that's up in here is what? Well, it's actually just 2. Okay, so if I go to my chart of values right here, if I jump into the cube chart, gosh, is there anything that we can do to break 2 down in terms of perfect cubes? No. Okay, so here's what I'm going to tell you. When you do problems like this, you're going to start out with a root. Start out with a big root right here. And we're still going to have which root?
3.
Okay, is there anything I can do to the 2 in terms of breaking it down into cube roots? No. Absolutely nothing. Okay? Now, listen to this carefully. There's nothing I can do to the 2, so it stays underneath the radical sign. The next part here, though, kids, is a to the what power? Okay. If I had a to the 13th, kids, how many a's is that really? So I'm going to list them all. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? The question really becomes this. A to the 13th power. We're trying to find perfect cubes of a to the 13th. In other words, how many triads of a's can I take out of here? Well, one perfect cube would be a to the 3rd. Can I take a to the 3rd out right away? How many more times can I take 3 a's out? And why am I choosing 3 again? Well, because we're looking for which root. Okay? Think of it this way. How many sets of 3 a's can I take out, or a to the 3rds, if you will?
4.
I took out how many?
4.
Okay. Think of it this way. How many times will 3 divide into 13 even? Wholly, I should say. 4. Is there going to be a remainder? How many? Okay. Think of that like 4, remainder 1, as saying, okay, if I take the cube root of a to the 13th, that's really this a to the 4th out front in simplest form. What was the remainder, kids? Is this last a going to group up with another group that isn't used up already? No. So how many a's were left over here, guys? That a to the 1st power goes back underneath the root. Okay? Why a to the 4th out front, kids? How many groups of a cubed could I pull out? 4. Does that make sense? Do the same thing for b now, guys. How many times will 3 go into that exponent of 3? 1 time. Is there going to be a remainder?
No.
So I can put b to the 1st out front. Do I need to put any b underneath the radical sign? No, because there wasn't a remainder. Okay? What's the exponent for c, kids?
8.
8. How many whole times will 3 go into 8?
20.
So what do you think you're going to put out front? C to the
2.
second, but is there a remainder when I take 3 into 8?
2.
2. So what's going to go back under here? C to the second. So your final answer is a to the fourth. Where'd the a to the fourth come from again, kids? Where did a to the fourth come in? 3 could go into 13 how many whole times? 4. Okay. Where'd the b to the first power come from? 3 goes into 3 1 whole time. Where'd the c to the second come from?
C going into 8. No.
3 into 8 how many whole times? Okay. Now,
2.
why did the 2 stay underneath the root?
Just because you can.
There's no perfect cubes to take out of 2. Exactly. Why is there an a left up in here?
Because it's a remainder.
Its remainder was 1. Was there a remainder for b's? Was there a remainder for c's? There it is, kids. Upper level stuff, absolutely. Impossible? No. Okay. Are there going to be some questions on this stuff? Absolutely. Sam? Absolutely. Okay. So same thing here again, kids. Yeah, Ellie. Yes, I do. You guys are catching me big time. Okay. Yep, thanks. I forgot that cube root there. Excellent observation, Ellie. Give yourself a pat on the back. That's awesome. If Ellie's move was a finishing backflip kick, I'd be on floor right now because that was awesome. Okay. We don't like roots where when we simplify stuff, kids. We do not like them in the bottom. Do I have that situation in the bottom? Uh-oh. Okay, no problem. First of all, we're going to kind of apply what we just did. Take a look at the bottom. How many y's in there for the radicand, kids? Y to the what? 13. How many times will 3 go into 13? 4 times with the remainder of what?
1.
Well, what if we could go just above the 4, remainder 1, up to a whole value of 5, okay? How many y's would you need? Y to the what power, in other words, to make 3 go in there 5 full times? How many y's do you really have right here, kids? Here's how you handle something like this. You say, okay, I know that by this right here, in a fraction form like this, to get this radical to go away, I know that 3 will go in here 4 times remainder 1. So what I would really love to have happen is to make this 3 go in here a whole number 5 times. Okay? What number divisible by 3 would make 5? So I need to make this y to the 13th a y to the what somehow? So how many more y's do I really need here, kids? If there's 13 here already, how many more do I need? So what I'm going to do is multiply by a form of 1. We're going to multiply by the cube root of y to the... I've got 13. How many more do I need to get to 15? 2 more. Why am I putting a 2 in here? Because when I combine these two, this is going to become the cube root of y to the what now? Okay, and up top, if I'm multiplying by a form of 1, what do I need to put up top? Cube root of... Okay, watch what happens. We get x to the second times the cube root of y squared all over the cube root now of what, kids? Yeah, cube root of y to the 15. But, just like in the previous example, we're going to look at this bottom and say, oh, how many times is 3 going to go into that 15? So this y to the 5th is just going to pull out in front. Is there any remainder to go back under a sign? If there's nothing to go back under a sign, is there really a sign down in the denominator anymore? No, it's just gone. And is that a good thing or is that a bad thing? That is such a good thing. That is such a good thing. So here's what you have. You have, as a solution,
Where should I put it, kids? Give me a second. I'll make some room. This is going to equal the following. It'll equal x squared. There's nothing I can do with the cube root of y squared because will 3 even go into 2, kids? Nope. So you just have to leave it as the cube root of y squared. Radicals up top, okay?
Yeah.
What's the bottom going to become? There it is. Done. I'm done. Oh, it's so cool. Okay, next one's not too difficult. If you can handle those two, you've got everything taken care of. If you can handle those last 2 examples and make sense of what the heck's going on there, you've got this handled. No problem. Okay? Now this stuff right here is pretty easy. This stuff when you have like x's above x's and y's above y's and z's to the negative power, this turns out to be pretty good. Anytime you simplify something though, you want your exponents always to be positive. Okay? Here's how you handle something like this. Look at the 16 over 8. Does 16 over 8 simplify, kids? 16 over the 8 simplifies to a 2. So I could say, well, that's going to turn out to be 2. Now, how about the x over x to the 2/3, kids? Those are like terms, like bases of x. That x up top is really x to what power, kids? So if I look at the x over x to the 2/3, guys, when you divide like bases, what do you do to exponents? Subtract, what's 1 minus 2/3? So this becomes x to the 1/3. Okay. There's some y's, guys. There's a y up top, but no y in the bottom. So times y to the what? Now here's the deal. I've accounted for the 2. The 2 came from 16 over 8. I've accounted for the x to the 1/3 by combining those. Y was itself. Z has a problem. And the problem with Z is what?
It's negative.
The exponent's negative. Okay, you guys know how to change, and I hope you know this. If you don't, I'm going to make this very simple. If an exponent is negative on one side of a fraction bar, where's the z to the negative 4 at? Is it up top or in the bottom? If it's negative on one side, it has to be what on the opposite side? Positive. So if I want that z to negative 4 to change to a positive, where am I going to move the damn thing to? Up top, right? Right?
Yeah.
So what am I going to do then? If I move this to the top, I'm just going to circle this thing and say, you know what? This thing goes up here as what? Okay. Let's see. 2x to the 1/3, y to the 1/3. That was all stuff that's still up top here. So what am I going to put tail there?
X to the 4.
Ooh, not x. Z. Okay. Don't discriminate z. All right. Just because it's last doesn't mean it's dead last.
Oh, I forgot the square.
Well, Sam, I'm sorry.
Don't cry, Parson.
It's okay. It's okay, Z.
I cry enough.
You and I have a lot in common.
It's fine.
We're almost done, kids. Believe it or not, we're almost done. I was going to give you a quick quiz today. How crazy was I thinking today? Let's get this last example done quickly. Last example is really pretty easy. Perform each indicated operation. We've done this already. What's true about the indices and the radicans here, kids? So what is this going to be? 6 of this mess plus 2 of the same mess.
8 of this mess.
There it is. Index the same on these two? Index the same on these two? I don't know. I just make sure you're paying attention, P. Yeah, like that.
Maybe you're having a
What if I told you I didn't sleep much last night? Would you believe me? I've had too much coffee to try and stay awake. Okay. Hey,
I think we have time to finish this last one up. Let's roll. Okay. Kind of the same game right here, kids. Are my indexes the same here for each power? They are. But the problem is the radicand down here. 3p to the 6th and 48p to the second. So let's work this right here, okay? I'm looking at the p to the sixth and the p to the second part. We've eventually got to get those to match, okay? So take a look right here. Guys, how many times will 4 go into this 6 right here? 1 time. So do you guys agree that this is like 16p times, what would the remainder be here?
2.
Times the 4th root of 3p squared, right? You guys agree with that? Okay, then minus. All right. Can 4 go into 2 here at all? No. But we better check and see if we can find a 4th root of what?
48.
Is there a 4th root that goes evenly into 48? How many times?
3.
Okay, so this is going to be, okay, so this is going to be p times the 4th root of 16 times the 4th root. How many times did 16 go into 48? 3. But what else is still under here with the 3? P to the what? Okay. What is the 4th root of 16 when you look at your chart? It's 2, isn't it? This mess right here is 2. So this is minus 2p times the 4th root of 3p squared. Guys, check out your index and your radicand now. Same or different?
They're the same.
They're the same. So if they're the same, can we combine? I've got 16p of this mess minus 2p of this mess. What's the 16p minus 2p going to make? So this will simplify to 14p times what, kids?
3p.
Such good stuff.